So this is the section 4.4 that we're talking about the multiplication rule and just the basics of it. We'll do the rest of it next class. But the basic idea is that if you are using the multiplication rule to find the probability of A and B, which is the probability of event A occurring and then event B occurring, you always have to consider whether or not the fact that A did occur affects the probability of B. And so, for example, if you are choosing cards from a deck of cards and you pick a king, then when you go to pick again, you have to consider the fact that that king now has changed the probability for your next pick. So if you want the probability you'll pick a king again, instead of 4 out of 52, it'll only be 3 out of 51. So you have to think about what A does to B's probability. Notation-wise, what you want to be aware of is that there is this conditional probability, is what this is called. And conditional probability means this little line is representing the fact that A has occurred. So you would read this as the probability that B will occur given A has occurred. And so that gives you that idea of making sure that you think about what the probability of B is, since it's the second thing that's going to happen. We have to know what happened first. So if we pick the card and we don't look at it and we don't know what it is, then we're going to have a hard time figuring out this, because we need to know what A is and what occurred in that first trial. So the formula then to figure out the probability of A and B happening, and you can replace that word and in your mind with both, so both things have to happen, is the probability that A happens times the probability that B happens given A happened. And multiplication makes sense here because if you think about multiplying fractions that are between 0 and 1, which is what probabilities are, when you multiply them, you get a smaller number. And so for both things to happen, the probability will be less than for either one happening on its own. So that's why the multiplication makes sense here. Intuitively, you're trying to figure out the probability that A will occur, and then once you know that, you're going to multiply on now the probability that B will occur, knowing that A did, and that's how you're going to get the probability of both of them occurring. So again, the multiplication is intuitive because it's making the probability smaller. You always want to make sure that you take into account whether or not A occurring has an effect on the probability of B. And if it does, then those events are dependent. So they will be independent if the probability of B is not changed by the first trial, by what happens in the first trial. And so if I put the card back in the deck before my second pick, then those picks are independent. It doesn't matter what happened first because I put it back. So we always have to think about that before we go ahead and try to calculate. And this works for multiple occurrences. So if I want A and B and C to occur, I need to multiply on their probabilities, always considering as I go through event to event to event whether my probability is changing or not based on what happened before. So again, dependent, independent. We need to make sure that we realize which situation we're in. If the one event does not impact the probability of the other, we'll say they're independent events. If one event does impact the probability of another, then they're dependent events. But that doesn't mean that one is causing the other. So this goes back to that question on the test, and that idea that just because two things are correlated does not mean that one is causing the other. There's just some kind of a relationship that we've got to be aware of. So there are times, though, where the idea of dealing with dependent events becomes very, very cumbersome mathematically. So, and if that's the situation, there sometimes it is okay to take dependent events and pretend that they're independent. But that's only when you're picking very small samples from very large populations. So the idea would be if I took 5 people from 1 million and I didn't put them back in the mix, it would be very rare to select any of those 5 again anyway. So whether I put them back and I count it out of 1 million, or I don't put them back and I count them out of 5 less than 1 million, is not making a huge difference. But how do you make that decision? Well, we have a rule. It's called the 5% guideline. So if your sample size is no more than, which means less than or equal to, 5% of the population size, which remember we use capital N for that, then it's okay to treat the selections as if they were independent and not deal with the conditional probabilities. Okay, so this is going to be our guideline when we look to do that. So an example, if we have 50 people, we're randomly selecting 2 of them and not putting the person back in the mix after selecting them. I want the probability the first person is positive or tested positive and the second person tested negative. So this and is going to tell me that I need to multiply. So the first person positive, tested positive, there are 44 of those out of 50 total people. So there's my probability that if I pick one person, that person will have tested positive. Now I have to look at the second person, knowing that the person I picked here is out of the mix. So now I only have 49 people, and I only have 43 that are positive, but I still have 6 that are negative because I didn't pick a negative person, negative test result person. So now when I do the probability, I'm going to use these numbers, and I'm going to say 6 out of 49. That's the probability. The second person will be negative. And for both of these to happen at the same time, I need to multiply them. So I'm multiplying the 2 probabilities and getting 0.108. So another example could be if we took 2 different people from our class and we wanted to find the probability, assuming that birthdays occur on the same day of the week with equal frequency. So just as many birthdays occur on Sunday, Monday, Tuesday, Wednesday, and so on. What would the probability that 2 people will be born on the same day of the week? And then changing it a little bit, that 2 people are born on Monday. So there's a distinction between the two. 2 people born on the same day of the week, they didn't say what day. So the first person that we think about could be born on any day. And so that means he just has to be born, and that means that the probability that the first person is born is certainty, and we could say that's the number 1. But now for the second probability, the second person born on the same day, well, now that probability is just 1 out of 7. Because whatever day the first person was born, the second one has to be born that same day. So I'm taking 1 times 1 over 7, and I'm getting 1 over 7. But if I'm trying to be specific about Monday, well, the first person and the second person's births are independent of each other. The fact that the first person's born on Monday does not affect the day the second person will be born. So they're independent, and they're each 1/7. So now the probability the first person's born on Monday times the probability the second person's born on Monday is 1 out of 49. Independent events. Sometimes when you have a problem that you're trying to figure out, it's easier to look at it in terms of a tree diagram because there's so many possible outcomes and it's hard to keep them straight. So if you want a picture of the situation, you can take a look at the picture of what it would look like to take a test where the first question is true, false, and the second question is multiple choice. So all the possible outcomes would be I answer true, and then for my second one, I answer one of these 5. Or if I didn't answer true, then I answered false, and then I answered one of those 5. So I've got a picture of what these 10 outcomes look like. And then a lot of times it's all about, well, how many possible outcomes are there? So this would tell me there would be 10 possible ways to answer this question. And that might be helpful information if I'm trying to figure out maybe what's the probability if I guessed on both that I would be right. And that would be, there's only one right way out of all 10 possibilities. So I could figure that probability out. So in summary, the addition rule that we learned before is for the word or. If I want to know the probability of A or B happening, since this makes it more likely when you use the word or, more successes, you're going to add the probabilities together, and that makes it larger. If you are using the word and you try to do the probability of A and B, that's less likely than either A or B. So we're multiplying the probabilities, and that makes it smaller. So there is a little diagram too that you can take a look at either in the book or on your spreadsheet. It says if you are trying to apply the multiplication rule, so you know you want an and situation, first decide if they are dependent or independent. So if they are independent, just multiply the two probabilities together. You don't have to worry about conditional. If they're dependent, you have to consider the conditional probability. And so that means that you have to think more carefully about this probability. So I wanted to finish off with just a few examples just to work through in case you're having trouble with this concept. I mean, some people do have some trouble with the idea of probability. And so for this first problem, you have 2 multiple choice questions, and each has 4 choices. So the situation would look like, in a tree diagram, you'd have 4 branches for the first, and off of each of those, you'd have 4 more branches. So you can picture how many possible outcomes there are if you just had to guess. There would be a lot of different guesses. In fact, there would be 16 different ways that you could answer the first and the second. But if we are just talking about the probability that we get the first one right, so we'd only be looking at these branches, 1 out of 4. Or the second one right, we'd only be looking at this branch. We've already taken care of this. We're just looking at the second question. So we're looking at pieces of the branches when we say or. So the probability that the first one is right is 1 out of 4 if I just guess. And the probability that the second is right is also 1 out of 4. And because it says or, I'm going to add and get 1/2. So 50% of the time, I'll get one of the 2 correct if I guess. To get both of them right, well, this is an and. And these are independent events. I have a 1 in 4 chance of getting the first one right, and a 1 in 4 chance of getting the second one right. So I only have a 1 in 16 chance of getting them both right, because only one of these branches ends in both of them being right. So 1 out of all the 16. There's a drug test at work, and 56 people test positive, 2,450 test negative. This is a little more realistic than the PowerPoint. If there are 4 false positives and 2,240 true negatives, what's the probability a person tests negative when he is a drug user? Well, in order to do this, I really need to see the data in a table. So I would want to say the people who test positive and the people who test negative. And then I'd also want to know the people that are positive and the people that are negative. So the people who tested positive are 56 people. And some of them are and some of them are not. So I'm going to put the total here as 56. And the people that tested negative, that was the 2,450. So I know how many people there are in total. There are 3,000 and, oh yeah, I can add 60. So try that again. 3,506. There are 4 false positives. Now, false positive would mean you tested positive, but you're really negative. So that's what a false positive means, and that means there were 52 true positives. And there were 2,240 true negatives, which means they tested negative and they are negative. So then I can subtract to figure out how many people tested negative, but they were really positive. So I'm going to have to take this minus that and get 210. So knowing the totals, I can back myself into this table, and that's going to help me answer this question. What's the probability a person tests negative when he is a drug user? So this when makes that conditional probability. He is a drug user. Those are the only people I'm allowed to use. So that would be this column. These are the people that are drug users. They are positive. And so that column would be my what I want to use on the bottom here, my total number of possible outcomes. So 262. But I want to know the probability that they test negative. So that would be these 210. So 210 out of the 262 drug users test negative. And that, then I can come up with a value for that and see whether I think that's acceptable or not, based on my test. All right, moving on. A deck of cards. I want to know the probability I'll pick an ace and then a king if there is replacement. So this makes them independent. And I can figure out the probability I'll pick an ace. And there are 4 aces out of the 52 cards, but that reduces to 1/13. And there are 4 kings out of the 52 cards. So that's also 1 out of 13. So I multiply it together and I get 1 out of 169. That's the probability I would pick an ace and then a king if I put the card back. If I don't put the card back, now they are dependent. Doesn't change my first probability, but it will change my second, because now there are 4 kings still, because I picked an ace, but there's only 4 out of 51. And so I'm going to multiply these two together to get my answer. And I don't have my calculator nearby, so I'll let you do that. The probability a woman has 3 girls in a row. So this is 3 probabilities multiplied together. But they are independent of each other. Just because you have a girl, it doesn't change the probability that your next baby will be a girl. So we're going to assume they're independent of each other. Each of them are 1/2. So the probability I'll have a girl, and then I'll have another girl, and then I'll have another girl is 1 out of 8. If I know that the probability that something I'm going to buy is defective is 0.025, the way I can figure out the probability out of 5 units chosen, I don't have any defects, then I need the complement. So if the probability of a defect is 0.025, the probability of a non-defect, or the probability, let's say, of a good item is 0.975. That's called the complement of this. So the probability that it will not have a defect is this, and every one of these 5 has that same probability to not be defective. So my answer is really, to write it easier, 0.975 to the 5th. Because I have to not pick a defect, and not pick a defect, and do it again, and do it again, and do it again. And every time I say and, it's a multiplication problem. So, couple examples there for you of the ideas that we've been talking about so far. And we're going to build on that even more on Friday. But I do want you to try your stat lab before that.